Good morning, how are you? So I'm Raviroj Somvadee. I'm gonna present to you about the Sigma Delta ADC converter. This is on the project A of the digital electronic. Okay. So we need to say greeting word, good morning, Mikola. So now I'm going to present to you and show my presentation in PowerPoint. Here's this is Sigma Delta ADC converter. So now I'm gonna present to you about the outline. So the outline today we're gonna break to the breakdown first and operation of the Sigma Delta ADC application, and then gonna end up with conclusion. So the first thing is breakdown of that. So that is today's topic is talk about the Sigma Delta analog to digital converter. So now first we need to know about what is the analog to digital converter. That is the device to transform analog signal data to digital signal. For example, if we have the 12 volt, it will transfer to the binary. That is the digital data have a high low in sequence on the data here. And the block diagram it should be like that. Should have a input as a analog signal into that box here, that system ADC, and that will process the signal to get a high and low on the binary data at the end of the output. Okay, that is a meaning and definition of ADC. And the next thing we need to know about propagation delay in ADC system. So the first thing I'm going to present to you about that word oversampling. That is state of analog input signal that insert to the converter too fast. So each system have its own take time for process just only one signal. If that signal is come too fast, then the ability of that signal it will ignore or don't have any ability to convert the signal of all time. So it will give you the oversampling problem, and the outcome is not precision. That's the problem at right now. So to make it more precision, we should mix between the previous and current data by using that one integrator circuit. That is the heart and the key and all of the thing of the signal Delta ADC converter. So what it's gonna do is just like I say, the system can have ability to convert the signal for all the time, so that system need to mix between the previous and the current signal to mix together and then convert. Yeah, that it will help on the oversampling problem. So first invention is this idea have developed for nearly 1940 or 1950 in France, but to make it happen, the group of engineers built up in the US make the first prototype in 1974. So we need to thank for you guys effort about create the amazing ADC converter. So now I will move on to its operation. We here is a block diagram of the Sigma Delta ADC. So you have four components. The first thing is the input signal is come here to the different amplifier. That one is the sum of the two signal. The first thing is analog signal, and that one is the feedback on it. Here that's its output from the 1-bit DAC. So I will talk to you about in detail later. And that one is integrator, the hard key of that system to make that the previous and the current signal to sum it together. And then here comparator, that one you can see here is connect with the ground level, that is 0, and that one will produce 1-bit signal for the output here. Okay, I will show you in detail about that. So at here we got the same block diagram as I show you. Here is kind of analog signal here going to kind of different amplifier, and X1 is the output from that state, and the X1 is kind of like going to the indicator, and the output it should be X2 in here. What we is gonna do here, the indicator kind of like will add the value of the previous value and the current value to make it kind of like overcome the sampling problem, or overcome the oversampling problem. Yeah, and the next one is gonna be here. Comparator stage is kind of 0 volt here. That's reference here. If that one is not greater than here, it will kind of like generate a low level in digital signal level. If it's greater than 0, kind of that, or reference here, threshold here, it will produce a bit one, which is high level. So that is kind of like gonna be output here, and output is gonna feed back to here 1 bit DAC, digital to analog converter. So when the output from here is 0, that here will generate -1 to here, and when the output here is 1, it will generate 1 to here to something at here, and that one can kind of like make the system overcome the oversampling problem here. So now I will show you the flowchart about all the process on that. So X is kind of like input here, analog input. X is gonna be process the signal in kind of like different amplifier. So the output from that one is X1. X1 is equal to X, which is analog, minus F, XF, which is come from the feedback loop here. Yeah, 1 or -1, it depends on the output here, and then the output is X1 gonna flow into indicator. So what indicator do is sum the previous signal, maybe X initial plus X1, and that's gonna be X2 out of here is kind of like sum between the previous signal and now the signal is kind of like to make it overcome the oversampling problem, and that's X2 gonna move into comparator. What comparator do? Comparator will identify which signal is greater than the threshold or the kind of like the reference level of the signal, which is 0. So that one will split into two cases. The first case is when X2 is greater than 0, X3, which is the outcome of the signal, or no, outcome of the system. The X3 is gonna be 1 at a high level. And another case is kind of like when X2 is less than the reference value, which is 0, the output is gonna be the other, which is 0. And what it's gonna do? That is gonna move into the first step at the loop, at the cell, just the same as servo motor to do that. Yeah, that idea will solve the oversampling, which is the propagation delay of the converter signal. If signal is changed too fast, the signal will ignore on that moment that doesn't have ability to convert the signal all the time. That's why we need to have the indicator to mix the current signal and the previous signal, then converter to find the kind of the mean or the average of the signal in real time for more precision converter. That's why this ADC is give you kind of like a really high precision and noise shaping. That is how it works. And the application of this device is gonna be AD7714. That is a IC circuit that available in the market. Yeah, that use the idea of signal and delta converter to make it to be a low power 24-bit. Yeah, and have a really high precision. So this IC gonna apply to the instrument application, just like something to measure the value or transducer and give you kind of like a digital output to process in the microprocessor or another system. Yeah, the second application is AD20MSP41. Oh, that is a kind of GSM chipset that use the idea of the signal Delta ADC to make a bit more precision. Yeah, and it's kind of like a low power consumption because that idea is so simple and give you kind of like really high effective ability. Yeah, that's its application. So now I'm gonna end up with the conclusion in here. The first thing is Sigma Delta ADC is a kind of, this is solution for the oversampling and noise shaping. Yeah, just like I said before, every system have its own publication delay, so that we overcome this problem. And this characteristics lead the electronic industry to use this technology to develop one precision device. Sorry for that, I need to fix that later. Yeah, my bad. And majority of the application is lay on instrument and compact integral system, just like I show you at here. So very compact on the GSM chipset, and that one is kind of like a 24-bit and very high precision system. And that is the conclusion, and thank you for your attention. Yeah, okay, all good, thank you so much.